All right, let's do this. All right, guys. So the next unit, yay! Now we're into bonding. That's what we care about, right? B is for bonding. B is for bonding. So today we're going to talk about bondage between different atoms. Some atoms are stronger than others when they bond. And you learned that the most important general idea in all of physical science is that opposites do what? Attract. But similarly, likes do what? Repel. So today and tomorrow, we're going to talk about the attraction and repulsion both of atoms for each other and of molecules. So there is attraction of different atoms together and repulsion of different parts of the atom. And there's also attraction and repulsion of entire molecules. Now, let's just step back and remind ourselves what the difference between is of an atom and a molecule. Okay? An atom is one element. A molecule is more than one. Okay? Make sense? Okay. So, and cruising around the atom's nucleus, you will find a bunch of electrons. Like this sulfur atom has a bunch of rings. How many electrons in the first ring? 2. How many in the second ring? 8. And then this particular sulfur atom has 6 electrons in its outer ring. Now it's similar because it's in the same group as oxygen. Now oxygen also has 2 electrons in its inner shell, but then its outer shell only has 6, just like sulfur. So if you're oxygen, how many valence electrons do you have? 6. How many valence electrons do you want? 8. Yeah, you want 2 more, exactly. So if you're sulfur, which is right below oxygen, how many valence electrons do you have? 6. How many do you want? 8. So what is both sulfur and oxygen going to do to complete their octet? They're going to try to get 2 somehow. Okay? Ken, do you have a question?
I have a question, yes. Wait, so atoms aren't everything?
Yeah.
Cannon, what?
I was asking if atoms aren't everything.
Yes.
You should have been.
Atoms are everything. Everything that's not energy is atoms. Yes, everything's not energy is atoms. So a beam of light is not atoms because it's a photon of energy, but everything that's not energy.
Wait, so is atoms the things you eat?
Yes.
I was just making sure things.
Dude, you just got like 4 face palms at once. You got like a quadruple face palm. All right, so we got. I wish you could have seen what I saw. Like 4 of you went like. Andrew did a double face palm. Okay, so back to work, guys. Try to. He had a long weekend. He was playing tennis all weekend. All right, so back to work. So oxygen, guys, focus. I know you can do this. Oxygen has 6 valence electrons. It wants 2 more. Sulfur has 6 valence electrons. It wants 2 more. So they got some options. One option is to float along until another atom comes along that likes to give up electrons. Somewhere in here is my silver. Okay, so here's silver. Silver's cruising along, and silver has 1 outer electron. Silver is a metal. Oxygen's a non-metal. One option that we can do is silver can donate one of its electrons to oxygen. Okay? And that would have 7. And another silver would come along and donate another electron. And oxygen would have 8. So and then silver itself would lose its outer shell, become stable, and be happy. Both of them. And the compound you would form would have the formula Ag2O. Oxygen was is -2, and each oxygen or each silver is +1. So each silver ion or each silver atom lost an electron. Make sense?
Yes.
Making each of them +1. Oxygen gained 2 electrons, making it -2. Make sense? This is an ionic bond. when electrons are given or taken, that's an ionic bond. Because the ions are formed and then stick together. Ionic bond. They form and stick together. I wish I had another silver, but I didn't print up another silver because I printed one of everything. But imagine there's another silver, okay, connected to the oxygen. Make sense?
Yeah.
All right. Now, in addition, oxygen's got some options. Oxygen has 6 electrons, going back to normal oxygen atom. Sulfur also has 6 electrons. Oxygen needs 2, sulfur needs 2, and they can strike a deal. Oxygen can say to sulfur, "Hey, sulfur, if you let me borrow 2 electrons, I'll let you borrow my 2 electrons." And sulfur says, "That's a great idea. It would appear that I have 8 electrons. And it would appear that I have 8 electrons. How can we both have 8? Well, that makes sense because the electrons are zooming back and forth at the speed of light. So it appears that we both have 8. That's a great idea." See how this works? So I didn't plan this. So oxygen has 6 electrons, needs 2. Sulfur has 6 electrons, needs 2. So what happens is sulfur puts 2 in the pot that oxygen uses, and oxygen puts 2 in the pot that sulfur uses. And instead of one having 4 and the other having 8, because the electrons are zooming back and forth at the speed of light, it appears that they both have 8. Does that idea make sense?
Yes.
Okay, and that is covalent bonding. So the compound would just be SO, and guys, yeah, so SO, they don't have charges. They don't have plus and minus charges. They just share, exactly. So sulfur shares 2 electrons with oxygen. Oxygen shares 2 electrons with sulfur, and they form a covalent bond. Covalent bonds, would you imagine covalent bonds are stronger than ionic or weaker than ionic?
Stronger.
Stronger. They're
That's
stronger.
what he said.
Yeah. Covalent bonds are very, very strong. Okay? Does that make sense? Now, practically what really happens is because they are sharing and oxygen doesn't trust sulfur and sulfur doesn't trust oxygen, they want to get really close together. So they make sure that they don't lose their electrons. They're like, "Hey buddy, this isn't an ionic relationship. This is a covalent, we're sharing." But they don't trust each other, so they want to get close together. And ultimately, they want to obtain just the right relationship where oxygen's nucleus is sharing sulfur's electrons, and sulfur's nucleus is sharing oxygen's electrons, but they don't want to repel each other's electron clouds. Does that make sense? Remember in the video, it said, Heisenberg imagined the electrons in a cloud. Well, they want to get close enough together where this guy's nucleus is attracted to this guy's electrons, and this guy's nucleus is attracted to this guy's electrons, but they don't want to get so close that their electrons repel each other. So they attain a perfect distance that balances out that attraction and repulsion. Cool? All right. Questions?
No.
All right. And then, of course, with metals like silver and copper, what do D-block metals do? They delocalize the electrons. They share the electrons in a giant electron commune, man. We share it all. Can anyone truly own an electron? Remember the electron C model? So D-block metals share their electrons in a big hippie electron commune.
Oh, that's why you sound like a hippie. I was so confused.
And that's his intelligence.
Okay.
Like, why are you taking that picture?
So, oh, you wanted a picture of that?
Oh, yeah.
Okay. Here you go. Again, this is also on your tube. All right. So again, ionic bond, given or taken. Covalent bond shared between 1 or 2 atoms. A metallic bond shared between all of them. All right. So review, again, if you want to write down a review, you can. If you want to take pictures of a review, you can. I'm not going to spend very much time on it. Remember, an ion is what you get when you give or take away an electron. Okay. Positive or negative ions. The octet rule states that all atoms want 8 electrons. If they can't have 8, they'll lose electrons, so the next inner shell has 8. Remember our talking about collecting things? When I wrote this, Pokemon was the thing. Now nobody plays Pokemon. It's all about Magic the Gathering and Yu-Gi-Oh! You know, I thought that was cool. Anyway, and metal and non-metal, electron C. Cool? And remember, a positive ion is called a cation, and a negative ion is called an anion.
Anion.
Okay? If you want to call it cation and anion, I don't care. I'll just look down on you and your heritage. But a positive ion is called a cation, a negative ion is called an anion. So the typical example we use is forming a crystal of salt. So chlorine is not stable by itself because it has 7 outer electrons. It wants to get one more, and when it gets one more, it forms a chlorine -1 ion. And review, why is a chlorine -1 ion always larger than a chlorine ion, or chlorine atom?
Because anions are actually larger than their neutral atoms.
Why? And
The electrons repel each other, making the cloud bigger.
exactly, yeah. So more electrons means more electron-electron repulsion. Okay? More electrons means more electron-electron repulsion. Is that what you're going to say, Mackenzie? Is that what you're going to say?
Was I gonna say something?
I thought you had your hand up.
Oh, no.
I thought you got exasperated, like, darn it.
Kenny.
Okay. And then the other side of the coin is sodium. If sodium is going to form an ion, it's going to be a +1 ion by losing an electron. And why are cations always smaller than their neutral atom?
Because of the fact that the protons are pulling the electrons in more, so the attraction's a lot greater. And that causes them to be smaller.
It's just the opposite. You have more electron-electron repulsion, less electron-electron repulsion.
No.
By losing an electron, you have less electron-electron repulsion. And sometimes, as in the case of sodium, you lose an entire outer shell. When sodium loses 1 electron, it loses the 3s1 electron. Make sense?
Yep.
Are you ready to move on? Okay. Moving on. Okay. So, ions are attracted to each other. It would be spectacular if you could see a single atom of, or single ion of chlorine and a single ion of sodium, but you can't. But if you get enough of them together, then a whole bunch of sodiums will be attracted to a whole bunch of chlorines, and a whole bunch of chlorines will be attracted to a whole bunch of sodiums, and what you get is those little cubes that you put on your French fries.
Wait, yes, I would. Oh,
Yeah.
Minions.
So
nice.
when you go to lunch today and you get your French fries, take a look at the salt crystals. If you look at them under a microscope, you will notice they have right angle edges. Yeah, ideally, cubes or rectangles, yeah. They form tiny cubes. And the reason they form tiny cubes is because the crystal lattice is an alternating pattern. It's chlorine, sodium, chlorine, sodium, chlorine, sodium. They form this grid that is a perfect 1-to-1 grid. Okay? Kind of like a checkerboard. A checkerboard goes black, white, or red, white, or black, red. A chessboard goes white, black, white. It's a perfect grid.
Yeah.
Well, sodium and chlorine make a perfect grid called a crystal lattice. Yeah.
Wait, is crystal lattice only salt?
No, all ions that form solids will form a crystal lattice. So a lot of the chemicals that I use in the back that are solids, they're basically ions that are stuck together. They will also form crystal
Squares?
lattice.
Which are squares? They're always going to be squares, right?
No, they're not always squares. So Cannon asked a good question. Okay, he asked if all crystal lattices were squares, and the answer is no. They're not all squares, because sometimes the pattern isn't like a checkerboard. The reason we use this pattern, because it is a checkerboard, is this is something that we all recognize. But if you find crystals of quartz, if you go into the mountains and you dig up some quartz, quartz has this shape. Yeah. I should have drawn this one. This one gets confusing. Take that one out of there. Okay. So quartz crystals form hexagons, and if there are crazy places that I've never been, but I've seen them in pictures. There are crazy like beaches where crystals have formed out of the ocean water. Basically, minerals have dried, and they form these hexagonal columns because some salts form hexagons. Some salts form diamonds, like diamond shapes, like rhombi. Question? It is, and ice is actually a hexagon as well. And we'll talk about ice a little bit later. All right, so when solid ionic compounds dissolve, they form electrolytes. When solid ionic compounds dissolve, they form electrolytes. Does anyone remember what an electrolyte is?
It's in Gatorade.
It's in Gatorade, yeah, it's Brondo. Yeah, that doesn't tell me what an electrolyte is. What's an electrolyte, Matthew? Close. Exactly. If you look about one page back in your notes, you'll find that electrolytes are solutions that conduct electricity. You guys are so indoctrinated into modern marketing. Wow. Electrolyte, Gatorade. But yeah, so Gatorade has electrolytes. Your sweat is an electrolyte. Your blood's an electrolyte. Your tears are electrolytes. There are solutions that conduct electricity, and they conduct electricity because they have in them ions. Come on, office. You can do it. Yeah.
When an ionic substance such as sodium chloride.
Guys, this is hugely important. Pay attention. Despite the video being 20 years old, it's super important. Okay, so this is a salt crystal. It's still too small to actually see. In order to see it, you need hundreds of millions of salt ions. But imagine you put a crystal in water. How does it dissolve?
It breaks down.
It breaks down. It breaks down into its ions, right? Ow.
If you put water on it, the water breaks it. Oh, I did something right.
You did something right. Exactly right. Watch this. It's very important. So the front row, very engaged, doing a great job, going to be successful. You're probably all going to have to call them sir and ma'am at some point. They realize that water is polar. Remember from the video? Water is polar. And we'll talk more about polar later. So watch what happens when water molecules approach the salt crystal.
When an ionic substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice.
Did you hear that? Lattice. If the salt is soluble, the electrostatic retraction between parts of the water molecule will break the crystal apart. In other words, if the crystal is weaker, if the crystal lattice is weaker than the water molecules, the molecules will, or the ions will dissolve.
Solvated ions move off the surface and become separated in solution. Notice that water molecules.
This is huge. All right. These are water molecules. That's a chlorine ion and that's a sodium ion. Not to scale. The sodium would be like tiny, but not to scale. That's a chlorine ion, that's a sodium ion. Notice how the water molecules have arranged themselves around the ion. It does this because water is polar. What do you mean by polar, Mr. Byers? Well, I'm glad you asked. If you draw water, the water molecule, it's an oxygen and a hydrogen and a hydrogen. And for reasons I'm going to get to in a little bit, let me put a dot here and a dot here, and a dot here and a dot here. If you were to look at water molecules like you look at a magnet, you see a magnet, and a magnet, for reasons that I'll teach you if you take physics, has a north pole and a south pole. Okay? And there's magnetic lines that go from the north pole to the south pole. Well, similarly, if you were to draw the electron clouds around a water molecule, they would look something like this. So, where are most of the electrons?
On top or on the bottom?
Down here. Most of the electrons are down here. So we give it a partial negative charge. And if there's a partial negative charge here, just like there's a south pole, then up there should be a what? A partial positive charge. Just like you can't have a magnet with only one pole. You know this, right? If you have a magnet that has a north and a south, you crack it in half, now you have two norths and two souths. Okay? You can't have a north without a south. And you can't have a partial negative without a partial positive. So water is polar. The hydrogen side is attracted to the anion. The oxygen side is attracted to the cation. Does that make sense?
Yeah.
Shall we move on? Okay, if this makes sense, excuse me, if this makes sense, you give me thumbs up. Okay. If you want to talk about it some more, wave your hand around. All right, moving on. I'm going to back the video up just a tad.
Attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
A lot to unpack in that video. I hope you paid attention. All right. The actual lowest ratio for a crystal is called the formula unit. Okay. So when you have a big pile of sodium chloride and you reduce it down to its base ions, you get an NaCl. Okay. That's the formula unit. And then the formula unit, the chemical formula of the formula unit is the empirical formula, NaCl. Okay.